So yeah, thank you for introducing me, and thank Derek for inviting me. I know Derek very well because I was there when he finished his PhD thesis with Simon. So thank you. I'm now at the eScience Center in the Netherlands, and some of you know that, but it's quite a young institute devoted to supporting scientists in their e-science and computational science struggles. And I've done this work with a lot of people, even more people than are here, and I'll thank them all. So I'll talk to you about the multiphysics and multiscale framework we've built and what our plans are with that. Now, the reason for this is really simple. When I think back to my thesis work, I did simulations of dwarf galaxies, and it was always a struggle to run and analyze the simulations. And it is all a bit like this. And our idea is that running and doing computational experiments shouldn't be like building the pyramids, but more like building pyramids with Lego. And we need so our idea is that we need a method to interact with simulation codes that's really intuitive to use, and where you can work with different codes without knowing the particulars, the language, without going into in short, without going into the manual of the language, and it should also not be a chore to run codes in parallel or run them remotely on the supercomputers, for example. So the framework we came up with was our AMUSE and OMUSE, and the AMUSE is the astrophysical version of the multiscale and multiphysics framework, and OMUSE is for oceanography and climate science. And what they do is they provide a Python-based interface for with high-level object-oriented interfaces, and also high-level and modern data structures with integrated support for things like units and battery mappings. And it allows you to remotely run and start up in parallel an arbitrary number of instances of your models and have them communicate or interact in different ways that you can specify in your Python code. Now, a little bit of history. This OMUSE was started in the astrophysical modest community, which stands for modeling dense stellar systems, and they ran into this problem where they wanted to go beyond gravitational simulations. So they talked to the stellar evolution people and said, can we use your stellar evolution codes? And the stellar evolution people say, well, we're tired of stellar evolution, and why don't you give us your gravitational dynamics codes, and then we can incorporate them in our codes, and then we have very nice simulations. So out of that fight, the idea started that, well, all the codes that we need are already there. We just need to have a nice glue to have the different codes talk to each other. And out of that idea came AMUSE, and it was developed first with funding from NOVA and later on from the Dutch science funding agency mainly at Leiden Observatory. And by now it's a major package which is actually being used by about a dozen groups worldwide, and has resulted in publications and thesis. So most of Derek's colleagues actually worked on thesis having to do with AMUSE. You know yourself didn't. A little bit. Okay. Yeah, MUSE was it called back in the days. So around 2040, we started the project grew on us, and we started thinking like, can't we do this for other types of domains which encounter the same problems? And we talked to Henk Dijkstra from the IMO in Utrecht, and he was interested, and we started with funding from the Netherlands eScience Center, the project to generalize this approach for oceanography, and that was that became OMUSE. And OMUSE by now has an initial capability and is being used in a number of projects, and I'll give you an example of that. So, so AMUSE is a nice framework, but of course it incorporates codes, and this is basically an overview of all the codes that are currently in there. And the important thing to note is, apart from that, it's quite a long list by now, and even not all the codes are on here, is that the codes are codes from different domains, and the idea is that all the codes from a single domain have a similar or has the same interface, and different domains have a similar interface that are formulated along similar lines. And the initial domains that we started with are sort of still the most important domains for AMUSE. And OMUSE is a development from AMUSE in the sense that much of the development of OMUSE actually went right back to the trunk of AMUSE, and we improved quite a bit on the data representation side, where we improved the grid support and added automatic grid remappings and grid generation routines, which are much more important for Earth science applications than for astronomy, because typically in astronomy the grids are 3D and Cartesian, or at least that's what we supported. Well, that's not enough for Earth scientists. And of course, we also added a bunch of codes to OMUSE, and it's sort of a growing list. There's some not in here that are being worked on. And this sort of span the range of different, from simple conceptual models to quite detailed global models for the ocean, and also models for the atmosphere and local models for the atmosphere. So a nice selection of codes where you can do different things with, and where you can have them interact. So how do you talk to a code in AMUSE? Well, this is sort of the minimal Hello Universe example for AMUSE. And well, this is just standard Python, so you have your imports, and then you might specify your initial conditions. You instantiate the code. This is an important step, and if you want to instantiate it on some other machine, you add some keywords here to specify the communication channel and to specify the machine where your calculation will be done. And you initialize the model. You do some evolution. And at the end, you do your analysis. In this case, you print out simply the total energy. Now, this is not very different from a Hello Ocean script, so, but that's the whole idea. There's no surprises here. If you've seen the trick once, you know how to do it for any code that's in AMUSE or OMUSE. Now, that's not a simple behind the scenes. This is sort of the schema of the drawing of the interface design, where I sort of what you saw in the script was here on the user side, and this is a whole bunch of things that happen behind the scenes. At the end, there's a code running in your favorite parallelization paradigm, and you can interact with it. And the interface defines a number of services where things happen. So the first thing to note is that AMUSE and OMUSE are based on remote code interfaces. And these codes can be run in parallel, and calls can be asynchronous. The AMUSE provides a number of interface services, such as unit handling, data structures, and the code state. And I will not go into detail because I have no time for that. So the important part is that at the end, the user is presented with a uniform high-level interface, which easily integrates in your scientific Python workflow. So what can you do with it? Well, there are a lot of things you can do with it. You can basically, you all know that. Basically, of course, you can simplify your model setup and model runs. You can script the runs and do things like event detection, or check on the state of your simulation and stop it when it goes out bounds, which can happen in practice. You can add a data analysis to your running simulation, or do ensemble simulations and other things. So I'll skip this example of online data analysis. Talk a little bit about the code couplings that you can do with AMUSE, because one code is nice, but you want to have different codes talking to each other. And this is an example, a very simple example, where you force a ocean code with the wind stress coming from, in this case, from a file. And this is sort of the graphic that looks into that. So what you would want to do is you construct an object that looks like a running code, but doesn't actually do anything. It just reads in data from file, and then you have it interact with the code by sending out the wind stress to your code, and then this code can react with it. And in this way, you can set up quite more complicated interactions between the codes, where you have two-way couplings between your active components of your simulation. And you can see that it's not very difficult to write down in Python. So let me give you two actual example applications. The first one Gijs is going to talk about in a little bit, so I won't go into much detail, but it's an example of a two-way coupling between the small submodels and a large global atmospheric model. And it's a example where you have a lot of small model instances interacting with a larger code, and it's a nice example where you can do resolve the cloud in a global atmosphere model. So the second one is an example that has been worked on by Marta Saladino, and she's actually defending her thesis today. And she studied the simulations of HEB, so evolved stars, and the interaction of the wind with the companion. And this is quite a difficult problem, because the ultimate fate of this system depends a lot on the angular momentum balance, and you have to have very high precision for that. And it's a numerically challenging problem where you have different types of physics interacting to determine the outcome of the system, which can be a merger of the system or the exponential dissolution of the binary. And she set up a numerical experiment with AMUSE, and this was based on smooth particle hydrodynamics. And she really encountered this difficulty where the angular momentum evolution, the numerical evolution, determined the physical evolution of the system, which is, of course, not true. So she tracked down all the sinks and sources of angular momentum and made sure that the different swapped out different components to test the best combination, and so that we can really have a physical result rather than a numerical artifact. And so that was very important to be able to easily do that within AMUSE, and I think that's a good example where AMUSE really helped to solve a physics problem. So what are our lessons that we learned along the way? So the AMUSE development was really in a organic development, where we had, at the beginning we had a grand vision, but it changed a lot along the way, and that was because we was a mix of users and engineers that was working on the problem, which could quickly interact and quickly develop their ideas. And that was a good way of developing such a package, because you had commitment from the community, and it generated interest. Of course, a couple of things that were not so nice. It's still a little bit of a problem sometimes to get installation right, because there are so many packages involved. It can be tricky, and especially if you go to a supercomputer where some of the packages are not well developed. You encounter, for example, that the MPI implementation at the supercomputer, which is tailored to some super fast network, doesn't contain a implementation for the spawn command yet, and then so you have to work around things like that. But other than that, I think we are improving on these things. For example, we are simplifying the installation, where you can do just a pip install, and then you do an install of not all the components, but just the components that you need for the simulation that you want to do. And this ties in with a little bit of change in the way people use and manage scientific software, where this sort of thing it has become much easier in recent years. So the next steps are that we're developing a similar package for the water cycle project, which is a project in hydrology, where we want to have an online system for doing hydrological simulations and analyzing data. And this will just be a small part of this. And the important thing is that we're moving to interact with containerized models, which makes the installation even easier. And this is in hydrology, there's a standard for the interfaces, and we also can use that. So the architecture which we're moving towards looks a little bit like this, where you have a AMUSE framework, which contains the base, physics, and the logic that is the same across different domains. And then you have domain-specific packages, which contain, of course, the simulation codes that are specific to that domain, but also things like the units that are specific to that particular domain, or the coupling strategies that do not make sense in any other domain. You would also distribute with a package. And of course, things can move from here to there, and vice versa if you think that it makes more sense. So the challenges that we run into right now are really in the generalization, because we want to generalize the framework, and because we like having multiple balls in the air now, sometimes things collide a little bit, but that is nice now that we have the development at the eScience Center. It's not that the astronomy people have to reserve time because the hydrology people want to have some feature. I mean, there's not that would for sure be a problem, but now it's we have the sort of shared knowledge base at the eScience Center, which can solve problems and coordinate the development. Of course, we're not operating in vacuum, and we keep an eye open for where we can make connections with other packages. And of course, maintainability is always an issue, not only because we have sort of a bit rot of the code, where things start to break down because the compilers move on, but also people change the way in which they interact with the codes and how they develop these things. And this can be practical things like moving from SVN to GitHub, or other things in the way that you install and use these codes. And the goal is, of course, to make this our package what's called FAIR in data science. But basically means reproducible science. So, my conclusions. I think AMUSE and OMUSE have proved to be very versatile and very easy to use packages. The important thing and the nice thing is that you can write down quite complicated computational experiments in small scripts that you can give to colleagues, or for example, Simon has an idea, writes out a small script, and it hands it over to a PhD student, who then of course spends months in refining and doing the actual experiments. But it all starts out with a simple idea and a simple script, and that works quite well. And this approach works across different disciplines, and we're working at to really make this work for more domains and have it available for more people. Thank you.